Alright, let's go through a few functions and see if they're metrics. So, let's start with d1 xy equals x minus y squared. And I'll see here, I'll underline just to emphasize what we're working on. So let's see here. If we have the distance between so how do I want to do this? The distance between -1 and 1 is what? What is this distance? This is going to be -1 minus 1 squared, so that's going to be 4. The distance between -1 and 0 is going to be -1 minus 0 squared, which is 1. And the distance between 0 and 1 is going to be 0 minus 1 squared, which is also 1. So this means that the distance between -1 and 1 is 4, which is strictly greater than 2, but that's the distance between -1, 0, plus the distance between 0 and 1. These d's should have 1s by them. Hence, d1 is not a metric. And that is because it does not satisfy the triangle inequality. For the triangle inequality, this inequality here needs to be a less than or equal to always. And for all x, y, z, you need d1 of xy is less than or equal to d1 of xz plus d1 of zy. And that does not hold here for x equals -1, z equals 0, and y equals +1. So for that reason, d1 is not a metric. And of course, I had to resort to finding a counterexample for the triangle inequality because this function d1 is both positive and symmetric. Or not positive, but it's non-zero when x and y are non-equal, and it's 0 when x and y are equal. So, anyways, that's d1. So now we move on to d2, where we have the square root of x minus y. Let's see here. So obviously this is both it's always going to be positive because it's because absolute values are always positive and square roots are always positive. So the square root of norm of x minus y is always going to be positive. It's always going to be, if x equals y, then obviously it's 0. If x is not equal to y, then the absolute value of x here. So if x is not equal to y, then the norm of x minus y is strictly greater than 0, which implies that the square root of the norm of x minus y is greater than 0. Okay, so that confirms the first part of the first requirement for being a metric. The second part is symmetry, and symmetry obviously holds. And so, oh yeah, the first thing, that's positive definite, right? Because, well, that's for other things. Anyways, so yeah, so the first requirement satisfied. Second requirement, symmetry, obviously going to be satisfied because the absolute value function is symmetric. So for those first two ones, I'm usually just going to talk through those. I might write down a few things if necessary. But otherwise, I'll just talk through them because they're pretty straightforward most of the time. The last thing is the triangle inequality, and this is usually the one that works, that takes takes work. So lastly, if we have any x and y and z, norm of x minus y, well, this is, we do the standard thing that we do like all the time in this textbook is you take x and you subtract z and you add z in the middle here, and then we use the triangle inequality for the absolute value to write this like this. Okay, so now we've got the norm of x minus y being less than or equal to this thing. But now what I'm going to do is something sort of tricky. This thing is obviously going to be less than or equal to this, but I'm going to add an additional term here that I'm sort of just going to pull out of thin air. Z minus y plus norm of z minus y. So I've this 2 square root of whatever here. Whatever this stuff in here is, it's obviously going to be positive. So I'm just adding a positive term here, and so the this thing will get bigger, and so that's why I have this less than or equal to sign here. But now this is precisely equal to the square root of x minus z plus square root of z minus y, this entire thing squared. Because if you just FOIL this out, you'll get the thing that's above it. Okay, and therefore we just take the square root of both sides to get, let's see here, d2 of x, y equals the square root of norm of x minus y. And then this is less than or equal to, well, the square root of something squared is just whatever was inside the squared sign. And so we just have that. But this is, of course, d2 of xz plus d2 of zy. And therefore, d2 is a metric. Now, this is sort of a black magic proof, because if you're going through this exercise on your own and trying to figure out how to prove that d2 satisfies the triangle inequality, you're not going to pull this 2 square root of norm x minus z times norm z minus y out of thin air. You're not going to do that. What you're going to do is you're going to work backwards. You're going to start with this thing here. You need, okay, so we need d2 of xy to be less than or equal to d2xz plus d2zy. Okay, well, let's write that out. What does that mean? That means we need the square root of this thing to be less than or equal to the square root of this thing plus the square root of this thing. And then you'd be like, okay, well, what would that require? So let's square both sides of this and go from there. Then you'd square both sides, and eventually you would be able to work backwards and figure out, oh, we can just use the triangle inequality at the beginning here to actually get the thing that you desire. And so this sort of looks like a black magic proof, and usually when you have a black magic proof, what that means is that the way you come up with the proof is different from how you actually present the proof. And here the way you come up with the proof would be by working backwards. And there's other examples in this exercise where we do the same thing, where I do sort of some black magic calculations. Actually, in one of them, I think I just go through straightforward because it actually ends up being quicker. But anyways, this finishes D2. So now we move on to D3, and D3 of xy is the norm of x squared minus y squared. Let's see here. So it's obvious that if x equals y, then this is 0. If x is not equal to y, then x squared is not equal to... Oh. Interesting. Let x equal 1 and y equal -1, then the distance between x and y is going to be 1 squared, which is 1, minus negative 1 squared, which is 1, which is 0. So therefore, you have 2 points which are not equal, whose distance is 0. And that's not allowed in metrics. And so therefore, D3 is actually not a metric. Okay, that's interesting. Let me look back at D1 and D2 again. Okay, D1 we already said was not a metric. D2, let me just make sure that there's... Yeah, that can't happen in D2 because, like I said, I talked through... Yeah, I actually literally wrote it out. If x is not equal to y, then this thing must be strictly positive. Okay, so I'm really glad that I caught this because I did not have this written down. I had something else. But yeah, D3 is not a metric because it does not satisfy the first requirement of a metric. Okay, so that's D3. D4 of xy. Here, this is the norm of x minus 2y. And this should already, having like nothing in front of x and something in front of y, should immediately set off a red flag because metrics are supposed to be symmetric in some sense. Well, literally, like if you flip the x and the y, nothing should change. So seeing asymmetry in the formula should immediately set off a red flag to be like, okay, there's something not quite right here. And so indeed, if we have D4 of 1, 0, this is the norm of 1 minus 0, which is 1, and that is not equal to 2, but that is 2 is equal to 0 minus 2 times 1, which is the distance between 0 and 1. So the distance between 1 and 0 is not equal to the distance between 0 and 1, and therefore D4 is not a metric. Alright, and now all we have left is D5. And so this can't be too bad, can it? Right? Right? Please? Hopefully not. Please not bad? Please not too bad? It's bad. It's not great. The distance is the norm of x minus y over 1 plus the norm of x minus y. Okay. This is I think there's a slick way to do this proof. I think there is a very easy way to do this proof because I believe that, in fact, this is a very standard thing. If you have a metric, the thing about metric spaces is metric spaces can be infinite, like the real line. You can, given any integer capital N, you can always find 2 points which have distance greater than n from each other, and you just take -1 and n plus 1 or whatever. It's really easy to find that. However, if you want to make a distance function finite, you can do that. What you do is you make a new distance function, which is you take the distance between 2 points. Let's see here. The general thing is d prime is going to be d over 1 plus d. So d prime is your new distance function, and the new distance between x and y will be, you take the distance, you use your old metric to find your old metric d to find the distance between x and y, and then divide by 1 plus the distance between x and y. And if you do this, your metric space will go from being infinite to having any 2 points being at most distance 1 apart. Right, because if the distance d between 2 points is very large, then the 1 on the bottom of this fraction doesn't really change the fraction by much, and so the d prime distance will be very close to +1. It will be slightly less, but it will still be very close. This is sort of like what arctan does to the real line. and I think this is a standard topology exercise, is to prove that given any metric D, then defining a metric D prime like this will give you a metric, which is, in this case, finite. Or at least you can certainly do something like this with measures. But anyways, I recall running into things like this, and so I think there's a very general way to approach this type of problem, but here we don't have to do that. You can just do a really ugly calculation, and I decided to do that instead. So we want to prove, okay, well, first of all, so for all x, y, and z, that, okay, so obviously this is going to be, if you have x equal to y, then you're going to get 0 over 1 plus 0, which is 0. If x is not equal to y, then you have some positive number over 1 plus some positive number, which is some positive number. So that takes care of the first requirement. Second requirement, symmetry, is obvious because the absolute value of x minus y is symmetric, and so doing this to it is also symmetric. So the only thing we need to do for D5 is to prove the triangle inequality. So what do we want to prove? We want to prove that the norm of x minus y over 1 plus the norm of x minus y is less than or equal to the norm of x minus z, so the distance between x and z, plus the distance between z and y. And we're basically just going to do a whole bunch of computation here and verify this. Okay, so let's take the denominator on the left-hand side and multiply it through. So we're going to get 1 plus norm of x minus y times, and now let's combine these two terms and give them similar denominators. So we get x minus z times 1 plus z minus y plus norm of z minus y times 1 plus norm of x minus z. Whoa, yeah, my computer is not going to like this, and probably you might not either, because this is pretty computational and not very insightful, but it's a proof, so, oh well. And we're multiplying by 1 plus norm of z minus y. Okay, so remember, this is what we want to prove. Okay, so anyways, let's multiply that denominator over to the left-hand side. So we got x minus y times 1 plus x minus z times 1 plus z minus y. We want this to be less than or equal to 1 plus norm of x minus y times, and then we got, what do we got? We got norm of x minus z times 1 plus norm of z minus y plus norm of z minus y times 1 plus norm of x minus z. Close all our parentheses and brackets. Okay. And so now we just multiply everything out. And we'll do this over a few steps. We have to multiply this thingy out. Let's see here. Norm of x minus z. Oh, this is awful. Norm of x minus z plus norm of z minus y plus norm of x minus z times the norm of z minus y. And now this is less than or equal to, give myself a little more room just in case. 1 minus x minus y, 1 plus x minus y. Then we multiply by, see, we have x minus z plus x minus z times z minus y plus z minus y plus z minus y times x minus z. Okay. Now we got one more step here. Oh, one more really ugly step here. So anyways, we're going to multiply the left-hand side out. So we get x minus y times x minus z plus x minus y times z minus y plus x minus y times x minus z times z minus y. And this is going to be, we want this to be less than or equal to, and now we'll actually multiply this entire thing out. So let me just take, no, I gotta get the whole thing. Let's take this entire thing and copy and paste it, because when we multiply the 1 by this thing, it will remain. So we're going to take 1 times this, which will just be literally this. And then we need to add on this entire thing, but multiplied by the norm of x minus y. So we have x minus y norm times x minus z plus x minus y, x minus z, z minus y. Now we have x minus y and z minus y. Finally, we have x minus y times z minus y times x minus z. Okay, and then you sort of, when you get to this point, you just pray that you can cancel things. And that when you cancel things, it will all work out in the end. And that actually happens here. Okay, so we got this x minus y times x minus z here, which actually cancels with this thing. Okay, so those two go away. Okay, so that's gone. We have x minus y times z minus y. And that cancels with that. Then we got this third term here, x minus y, x minus z, z minus y. And that cancels with this one. Okay. So there we go. So we end up with norm of x minus y is less than or equal to x minus z plus x minus z times z minus y plus z minus y plus z minus y times x minus z. And so but what is this? This is equal to x minus z. And now we've actually got 2 x minus z times z minus y. So we've got 2x minus z times z minus y plus z minus y. And now, indeed, we have x minus y is less than or equal to, no, x minus y is equal to x minus z plus z minus y, which is less than or equal to x minus y plus z minus y by triangle inequality for absolute values. And now, if we add this 2 times x minus z times z minus y, that's only going to make things bigger. So this is obviously going to be less than or equal to this times x minus z times z minus y plus z minus y. Hence, d5 is a metric, because this confirms that d5 satisfies the triangle inequality. Now, how would I do this if I were trying to do like a this proof I've actually done doing it in the order in which you would actually figure out the proof. But how would you do it if you weren't sure? Well, what you would do is you would start it, or no, I said that wrong. how would you do this if you wanted to write up a really elegant black magic proof? What you would do is you would say x minus y equals norm of x minus z plus z minus y, which is less than or equal to this thing, which is less than or equal to this thing. This thing that I've written at the end here, this is what you would start with. And then you would work backwards through the really hairy computations that I've done, and work backwards until you get to d5 of xy is less than or equal to d5 of xz plus d5 of zy. And then you would say, therefore, we have completed the proof. So I've done this proof in the wrong order here to make it a little easier for me to write, but also to show you how you would come up with this. I guess it would take a little bit of like it took me a little bit of time to go from, okay, so we got norm of x minus y is less than or equal to norm x minus z plus 2 times this plus norm of z minus y. How do you get that by itself? It ends up being really straightforward from the triangle inequality for absolute values. But that is the only thing here that's like a little tricky to see how you would come up with that. But there you would just sort of mess around with the tools that you have at your disposal, and hopefully you'd eventually be able to come up with that. And like we saw in the other exercise, this norm of using the triangle inequality for absolute values ends up being really useful here. But yeah, hopefully this is a little enlightening in how you can do these sorts of metric exercises. Again, I think there might be a more general way of doing this that will work for any metric. But I don't know what it is off the top of my head. I would need to go back and review it a little bit. But this proof, while it's messy, it certainly does get the job done. And yeah, so we've gone through these 5 metrics. And let's see here. The second one and the 5th one were indeed metrics, and the other 3 were not. And that's what we were asked to determine, and so we are now done with this proof.